Hey everyone, this is my Teach the Doc for Chapter 9. So for the conversion table, just use this conversion of millimeters of mercury is equal to 133.322 pascals, and then just converting it to kilos of this kilopascals, using just our the prefix names, and then 680, so I was able to get 90.7 kilopascals. Torr is like 1-to-1 with millimeters of mercury, so that remain the same. And then 1 ATM is equal to 760 millimeters mercury, so just took what was given, which is the 680, divided it by 760 and got the 0.895 of ATM. So for these laws, supposing a gas has initial pressure of 2, what happens to the pressure if the volume is doubled? Assuming the temperature in moles remain unchanged, that's Boyle's law. So that means that the temperature will decrease because pressure and volume are inversely related at constants. So since the volume is doubled, the pressure will decrease as well. And then this third one ended up being Avogadro's law, which is saying that the moles and volume are directly proportional. So if the volume is going to, if the number of moles of gas is going to triple, then the volume will also triple with it. So it'll increase. On to this next page. So moles in the sample. So we needed to solve for N, which is the amount of moles. So just deriving that formula from PV equals nRT to N equals PV over RT, with our constant being that 0.08206 for R. 0.975 is the pressure, because you have to convert the millimeters of mercury to ATM. And then temperature goes to Kelvin, so that's the 298.15. Volume is already in liters, so that's fine. So setting that all up, you get to 0.0598 moles of the gas, or of that sample. And then for volume, you kind of just flip that formula again at STP. It's a little bit different, which is why I crossed out that first one, because I was just using the same info before. But for standard, or for STP, that means that Kelvin is going to be 273.15 and pressure is going to be 1. So just taking that 0.0598 from the first problem, plugging that into the equation there, and we get 1.34 liters of volume. Down here, just deriving density of gas to molar mass. So PV equals nRT, but then this time we're just doing molar mass similarity, so PV equals RT over M, and that can be flipped to being PM equals M over VRT, and then just further deriving that is PM equals DRT, then dividing the RT, you get D equals PM over RT for your derived equation there. For the bottom part, we are doing the molar mass of the gas if its density at STP is 0.901. So we know that density equals PM over RT from our derived equation before, but we were given density. So we're going to flip that and have it be molar mass is equal to density times RT over P. So that is equal to 0.901 times R is our constant, 273.15, which is our standard temperature, and then P is our standard pressure, which is 1. So that altogether is 20.18 grams per mole. On the back side, so it was asking which component exerts the highest partial pressure in a gaseous mixture that is made of half a mole of H2, 0.49 moles of O2, and 0.48 moles of CO2. And then the volume and temperature is just going to be assumed to be constant because they're mixed in the same area and they're not interacting with each other. And the partial pressure of each gas is related to the total pressure by the mole fraction. So just going by mole fraction alone, H2 will have the highest partial pressure because that has the most amount of moles in the sample. And then kind of the same thing with this other problem. So total pressure is equal to the sum of partial pressures, again, assuming that the gases do not interact and each gas will always obey its own PV equals nRT in this situation. So just like taking the gas laws into mind, the most amount of moles was answer C, which is the 0.6 moles of H2, the 3 moles of AR, and then the 0.7 moles of HE. So that will exert, oh my goodness, the highest total pressure in that 5-liter container if everything else stays standard. And then going down here, we're taking the mole fraction of each gas, so just converting 2 moles initially. So if we have 3 grams of hydrogen, this one actually took me a minute because I did not account for there being 2 hydrogen involved. So H2, so 3 grams of H2, converting that to moles. So the molar mass in 1 hydrogen is going to be 1.0, I think 7 is what I initially put, but it ended up actually needing to be 2.01568, so that gave us 1.5 moles. And then did the same thing with the nitrogen. Originally just only accounted for 1, but now we have 2 nitrogen, so it's 2 times 14.0067, which is 28.0134 grams. So taking that 14 over 28.0134 is 0.5 moles. And so then the for the mole fraction, you just take each mole divided by the total number of moles. So 1.5 moles over 2 is 0.75. So that is the mole fraction of hydrogen in there is 0.75. And then taking the 0.5 moles of nitrogen over 2 is going to be equal to 0.25 for the mole fraction of the nitrogen. I think I put that nicely down there. When I first did it wrong, it was still the same ratio, which makes sense with how it's set up. But then I had a lot of problems trying to calculate my partial pressure of each gas, and I couldn't figure out why it was wrong initially. And then I went back and I was like, oh my gosh, I'm not accounting for the diatomic molecules. So partial pressure of each gas. So sorry, moving down here. So for hydrogen, I just took the amount of moles, which just using our normal PV equals nRT, but then just adjusting that and driving that formula to be P equals nRT over V. So N being 1.5, R being our constant. T, it was 298.15. I just took that from the prior conversion of the first problem, divided by 25 liters, and that gets us 1.47 ATM of H2. And then just doing the same kind of formula for the nitrogen, it's 0.5 moles times the constant R times Kelvin over volume in liters, and that's 0.489 ATM of nitrogen. Thank you.